Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to show that the Lebesgue-Stieltjes measure is countably additive on a field over right semi-closed intervals. Now, two background videos that we're going to reference is BV1, that stands for Background Video 1, is extending the Lebesgue-Stieltjes measure to a field, and BV2 is continuity of a set function. Now, the theorem we're going to prove in this video is the set function mu defined in BV1, which is the Lebesgue-Stieltjes measure, is countably additive on the field, the closure of R, where R extended is the reals plus minus infinity and infinity. And this is done more for convention than anything. So the proof goes like this. Let's assume that the difference between f of infinity minus f of minus infinity is finite, finite. And that means that the measure, Lebesgue-Stieltjes measure, is finite. So let's let A1, A2 be decreasing sets. Oh, and these are right semi-closed intervals. That's what these sets are, such that they converge to the empty set. Now let's let AB be one of the intervals. So these intervals, they get smaller and smaller and smaller, and we're going to pick one of them, say this one, and it's it's going to be one of the intervals of AN. Now let's let A prime converge to A from the positive side. Then by right continuity of F, the mu of this set, which is defined as f of B minus f of A prime, converges to f of B minus f of A, right? The f is right continuous, and this converges to A from the right, so it means converges to f of A, which is the measure, mu of AB. So the measure of this interval converges to the measure of this interval. Now, as this gets closer and closer and closer to this, let's stop just before it reaches it. And then let's let Bn be that interval, such that the difference is really close, less than epsilon, over 2 to the minus n. But the closure of this interval that's getting really close to, AB, the closure of it is a subset of AN, which is, of course, the right semi-closed interval AB. Now, since the intersection of these closures is a subset of the intersection of AN, and this converges to the empty set, that says that this intersection converges to the empty set. Now, note that the infinite union of these sets forms an open covering of R. And right, because the BNs, they get smaller and smaller and smaller, so we're subtracting off a smaller amount each time. So these eventually, cover the extended real numbers. But by the Heine-Borel theorem, for some n, there exists a finite subcovering. So at some point, we can stop and say this covers it, and that's by the Heine-Borel theorem. And as in with most of these proofs, it's like how far do you go back and keep proving and proving and proving. So we're going to assume that you've seen that. And if there's enough comments that say, hey, prove that theorem, well, I'll prove that one too. But that says this covering is R, the extended R. Now, if we list out a few of that's this. So like R minus BK is really R intersect, the B1 complement. That's the same thing, all the way to, the R extended intersect BN complement. That's what the difference means. But if this is R, one of these has to be R, because when you intersect, it can only get a little bit smaller. So at some point, one of these is R, and the extended R. So that implies that this intersection, the complement of these, it goes to the empty set. Now this is just kind of another way to see it. We showed it up here, right, that it's the empty set. And so this is just I'm just trying to show it like a couple different ways. Now, the measure of AN, which is the sum of these two disjoint sets, so this set and this set are disjoint, so it's the addition of these, but this is the empty set, so this is 0. So we'll bring, so that equals this. But now this set here, now the ANs are decreasing sets to the empty set. Now this set, and this is, I always have to, pause the video and draw sets and circles and make it right in your mind. But because these are, decreasing sets, if we take the first one and subtract off A1 minus B1, there's a little piece there. And then we union it to A2 minus B2, there's another piece that we've added to it. And if we add those all the way to N, this set is larger than this set. So that means the measure of this larger set is greater than the measure of this set. So now the finite union of these sets is less than or equal to the sum of these sets. But we said the difference, we defined, or we created BK such that this difference is really, really small. Epsilon of 2 to the minus K. And we're adding up 1 to N. Well, this epsilon is not part of that index, so it will come out. And we're summing 1/2 plus 1/4, 1/8. And that limits to 1, but if we stop it in, that's less than 1. So all this is less than epsilon. And that's actually what we wanted to show, that the measure of AN goes in limit to 0. Now, since it's continuous from above, and one of the, thus it's countably additive, and that's what we proved in this background video too. But this is just one special case where the set measure is finite. So let's assume that it's infinite. So here, if f of infinity minus f of minus infinity is infinity, we're going to define a new f that kind of knocks down those tails. So we're going to call it f of n of x. So when x gets too big, say greater than n, we're just going to put n there. So it's f of n. And then when x is between minus n and n, then it's just f of x, whatever it is. But if we get too far negative, we're going to just stick in minus n here. We're going to kind of knock it back a little bit. So that's how we're going to define f of n of x. Now, if we, the measure, so the Lebesgue-Stieltjes measure, mu, we're going to subscript it in to meaning we're dealing with this f of n of x. That's really the difference, the Lebesgue-Stieltjes measure. So it's f of n of b minus fn of a. Now note that this measure goes to, as n goes to infinity, the Lebesgue-Stieltjes measure, right? So as n goes to infinity, f of n of x equals f of x. So in limit, these are exactly the same. Now let's let A1, A2 be disjoint sets that are elements of the field of these right semi-closed intervals, such that the union is also in that field. And then we'll call that union A. Now, by theorem in BV1, this was true, that if we have the infinite disjoint sets where the union is back in the field, then this property holds. And we proved that in BV1. So this infinite sum is less than or equal to the measure of A. Now there's two cases here. So if this infinite sum is infinity, that means mu of A is infinity. And actually then we're done. So hence mu is countably additive, right? So the limit of this function equals mu of A. And they're both, right, infinity, infinity. So now let's assume that it's finite. So if this sum is finite, then mu of A, we noted, is equal to the limit as n goes to infinity of mu n of A, right? The way that we define mu n up here, right? It goes to this. But the A can be thought of, the mu n of A can be thought of as this infinite sum of mu n of A. And that's because mu n is finite. Now, here, if this difference is greater than or equal to 0, and you can see that because this property holds. So if we subtract this to the other side, it's greater than or equal to 0. And that's what this represents. But mu of A, so this measure here is this. So if you take this into here, then this is this piece, right? So mu of A, which is this and here, is equal to this. So let's replace it in here. So right, because this can go to there and then it goes to there, and then that's the same as this. But notice that mu of n is greater than, I mean, this is the way we define mu of n, it's less than mu. And then so that means this is negative, or, less than or equal to 0. But it can't all be less than or equal to 0 and greater than or equal to 0. So as it says, it equals 0. So this equals 0, which means this equals 0. So then if we take that to the other side, it says that this infinite sum is mu of A. And that's what we wanted to show, that this is countably additive, and thus it's countably additive. And that's we proved the theorem. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.